Hi, my name is Rhien, and today I'm going to be talking about the Staudinger reaction. The Staudinger reaction involves the mild reduction of an azide to an amine. This reaction is a great way to produce primary amines, which can otherwise be difficult to access. So here's a bit of an overview of what we're going to be talking about in today's video. First, we'll talk about the history of the Staudinger reaction, how it was founded, when it was founded, and who made it all happen. Next, we'll talk about the mechanism, what actually happens during this reaction, and the steps involved to get to our final product. And lastly, we'll talk about applications of this reaction, why it's important not only in chemistry, but in the real world. First, let's talk about how this reaction came to be and who made it all happen. This is Hermann Staudinger. He's the founder of the Staudinger reaction, and the reason it has its name. He is an organic chemist from a small town in Germany called Worms. He is primarily known for his work in the discovery of polymers. In fact, the Staudinger reaction was not even his most well-known work. This is what he did in his early days. This timeline shows Staudinger's life chronologically. As mentioned, he was born in 1881 in Germany, where he spent his childhood and most of his early career. After completing secondary school, Staudinger attended the University of Halle and got both a master's degree and a PhD in organic chemistry. Interestingly, Staudinger began his studies pursuing a career in botany before he switched routes to chemistry. In 1912, Staudinger began lecturing at the Swiss Federal Institute of Technology in Zurich, Switzerland. It is here that he discovered the topic of today's video, the Staudinger reaction. This discovery occurred in 1919 alongside his colleague Lothar Meyer, when they discovered that azides reacted with phosphines to produce amines. Staudinger was awarded a Nobel Prize in Chemistry in 1953. Although his Nobel Prize was not for the discovery of the Staudinger reaction, it still goes to show just how influential of a chemist Hermann Staudinger was. Staudinger's work can be applied to several areas, including synthetic chemistry, biochemistry, and more, which we will take a look at a little later in this video. Now let's take a look at the mechanism, the steps involved, and how we get to our final amine product. In the Staudinger reaction, an azide reacts with triphenylphosphine, yielding the corresponding aminophosphorane intermediate. This intermediate is then quickly hydrolyzed in aqueous media, allowing the final product. This slide here shows our original reactant, our azide, and then an amine, the product of this reaction. But what else is involved in the reaction to make this happen? This is triphenylphosphine. It is a phosphorus atom with 3 phenyl groups attached, along with a single lone pair. Triphenylphosphine is a basic compound, and therefore it is going to act as a nucleophile in this reaction. Let's take a better look at how this reaction takes place. As you can see, I've got all of our reactants and our intermediates drawn out here. Let's use arrows to see how the electrons are going to move in this first step to create our aminophosphorane intermediate. First, we see that the phosphorus on our triphenylphosphine has a lone pair. This molecule is going to act as a nucleophile and attack the electrophilic nitrogen on the terminal end of the azide, breaking the nitrogen-nitrogen triple bond and attaching itself to the terminal end of our azo compound. This first step is possible due to the presence of a resonance structure on the azide, forming the terminal triple bond and making the middle nitrogen electron poor, which allows the triple bond electrons residing in the p orbital to move on to the middle nitrogen, eliminating its formal charge as a new bond forms between the nitrogen and phosphorus of triphenylphosphine. Next, a lone pair from our negatively charged nitrogen is going to bond with triphenylphosphine. This is referred to as cyclization, because of the way it forms a 4-membered ring, as we can see in the next molecule drawn. Finally, we will see a decomposition step, yielding our aminophosphorane intermediate. The decomposition of this 4-membered ring is highly favorable, due to the angle strain within the ring, as well as the nitrogen gas that is produced as a side product being very thermodynamically stable due to the formation of a triple bond. So, after our first step, we now have our aminophosphorane intermediate as well as N2 gas as a side product. The intermediate will then move on to the next step of the reaction. Once we have our intermediate, it can be reacted with a number of nucleophiles, the most common of which being water, as we will see in our example. Similar to in the first step, we will first see a nucleophilic attack. This time, water attacks phosphorus, breaking the phosphorus-nitrogen double bond and attaching itself to the molecule. Next, we will see a proton transfer occur, shifting the location of the hydrogen atoms to eliminate formal charges on the oxygen and nitrogen to prepare for the final step. You may have noticed that there are no arrows drawn for the proton transfer step. This is because we don't exactly know where these protons are coming from. Sometimes this proton transfer happens intramolecularly. Other times, the protons come from something else, like the solvent. That is why we refer to this step as proton transfer, and you cannot see any arrows. Finally, we see our leaving group dissociation. The nitrogen-phosphorus bond is broken, phosphine oxide leaves, and we are left with our final amine product. This reaction is favored as a very strong bond forms between oxygen and phosphorus in our leaving group. This hydrolysis can also be promoted through the use of an acidic catalyst, so adding a few drops of a non-nucleophilic acid can help this process occur. And there we have it. After our two main steps, we finally have our amine product. This showed how an azide was transferred to an amine by the use of the Staudinger reaction. Over the next couple of slides, we will take a look at how the Staudinger reaction can be applied in other fields and why this reaction is relevant to current research. As we've discussed, the main application of the Staudinger reaction is the formation of amines from azides, a mild reduction reaction which saves from the need of using highly reactive or toxic compounds, such as lithium aluminum hydride or thiol compounds, like 1,3-propane dithiol. The creation of primary amines is especially helpful as they are a very versatile synthetic tool. The modified version of the reaction, the Staudinger ligation, is also a very helpful tool to chemists as it facilitates the linkage of two molecules to each other. This is utilized in the process of bioconjugation, as adding azides to biomolecules through an amino derivative is relatively straightforward. This is shown on the next slide with a protein. This reaction shows applicability in the field of biochemistry, analytical chemistry, genomics, proteomics, and developmental biology by its functioning in the cross-linking of two products together, such as biomolecules and tags. A use of this reaction is shown in this slide. By modifying the original triphenylphosphine with a methyl ester, researchers hypothesized that a stable amide bond could form instead of the azyl ylide when conjugated to a biomolecule with an azide attached. What they found is that the reaction yielded exclusively the amide product, which opens the door for the use of this reaction in bioconjugation and intracellular tagging. As shown in the slide, the methyl ester modified phosphine can have a fluorescent probe attached, which can then react with the azide-tagged protein to observe its expression. In the original reaction, the researchers linked the phosphine compound to a sugar, sialic acid. Now that we have taken a look at the history, mechanism, and applications, we have a better understanding of the Staudinger reaction and how it can be useful in multiple biochemical fields. Thank you for watching.